What is robot kinematics? Jacobians Explained. Imagine watching a robotic arm move smoothly to pick up an object or assemble tiny parts. How does it know exactly where to go? That's where robot kinematics comes into play. It's the study of how robots move, focusing on the positions, speeds, and accelerations of their parts without worrying about the forces involved. Think of it as mapping out the robot's dance steps without caring about the music that makes it move. In robot kinematics, we look at the robot's links, which are the rigid parts, and the joints, which allow rotation or sliding. The goal is to understand how these parts work together to position the end effector, the part that interacts with the environment like a hand or tool. There are two main ways to analyze this. First is forward kinematics, where if you know the joint angles or displacements, you can figure out where the end effector is in space. It's like knowing the angles of your elbow and shoulder to see where your hand ends up. This helps in visualizing and simulating robot movements easily. The second method is inverse kinematics. Here, you start with a desired position and orientation for the end effector and work backwards to find the joint settings needed. This is more complex because it involves solving equations that may have multiple solutions or sometimes none at all. It's essential for controlling robots to perform specific tasks accurately, like reaching a particular point or following a path. Now, let's talk about Jacobians. These are mathematical tools that connect how fast the joints move to how fast the end effector moves. Imagine turning a steering wheel. Small turns result in the car moving in a certain direction. The Jacobian matrix captures this relationship. It tells us how tiny changes in joint angles or displacements affect the position and orientation of the end effector. This is super helpful for velocity analysis, where we want to know how quickly the robot's hand can reach a target or avoid obstacles. Jacobians also help identify singularities, positions where the robot loses some control or degrees of freedom. For example, when the robot's arm is stretched out straight, small joint movements might not produce much change in the end effector's position. Recognizing these points is vital to avoid issues during operation. Although kinematics ignores forces, Jacobians are used in dynamics to translate forces and torques at the end effector into the joint space, helping in control algorithms. In robotics engineering and development, understanding how joints and links move through kinematics and how Jacobians relate joint velocities to end effector velocities is key. It allows engineers to design precise, reliable robots for tasks like assembly, welding, or even surgery. By mastering these concepts, you can program robots to follow complex paths or perform delicate operations with high accuracy. So, in essence, robot kinematics and Jacobians are the backbone of controlling robotic motion, turning mathematical models into real-world movements.